So I will start. So welcome to the evening session of the third day of Amplitudes 2021. I hope you enjoyed your dinner and you'll also have a chance to have some after drinks in our virtual reception at Gathertown after this evening session. It will be a bring your own beer style. So it will be drinks of your own choosing in the most homey settings possible. For a couple of hours, so from 9 to 11 Central European Time. And now it is my pleasure to introduce Cindy Keeler from Arizona State University as our first speaker of the evening session. She will talk about the fascinating Weyl double copy and its application to fluids. Cindy, the floor is yours.
Hello, everyone, and thank you to the organizers for getting this set up, even if it is virtual this year. It's lovely to get to see all of you, and I appreciate the opportunity to speak. Today, I'll be talking about, as my slides say, the Navier-Stokes to Maxwell via Einstein. So we'll be using both the double copy and also fluid gravity duality. I do want to point out that as I'm coming from Arizona, it is actually still morning here. So good morning to anyone else for whom it is morning at the moment. And I will be talking today about work based mostly on a paper from last May, but also on some forthcoming work together with my student Nikhil Monga, who graduated last December, but also Tucker Manton, who will be on the postdoc market this fall. So you should look forward to seeing him there. All right, let's go ahead and get started. So we'll start with a brief review of the classical double copy via Weyl. And maybe mention a couple of new advances in that direction. And then I'll talk about from Navier-Stokes to Einstein, that is the fluid gravity duality. And then we'll talk about some particular cases of fluids where we understand well how the classical double copy story works. And I will conclude by talking about some work towards a general fluid. So let's go ahead and get started with talking about the classical double copy. As everybody here is very familiar with, of course, the double copy story takes the form of Yang-Mills amplitudes being rewritten in a particular sense as the square to give us gravitational amplitudes. And of course, we can also write a scalar theory with amplitudes given by just these CK factors. There is a nice review of the classical double copy in this large review by these folks here, particularly chapter 10, I believe, focuses on the classical double copy. So if you're interested in more details of the status as of the date when this review came out, that's a great place to look. I did want to briefly show what the Kerr-Child map looks like, because for people who are unfamiliar with the Weyl gravity story, this case is a little bit simpler to understand. So this first came out in 2014 with Ricardo and Donald and Chris. And basically the setup is, if you can write your metric in Kerr-Child coordinates are coordinates where you have flat space plus a scalar times k mu, k nu, or k is a vector that is null. So if there are coordinates where you can write your metric like this, then you can create a single copy of the double copy that is the gravitational field. So the gauge field becomes phi k, and even the scalar phi itself will solve the wave equation for scalars. By the way, just as a side note, the color factors that we'll be working with in this talk will always be trivial. That is not true for every version of the classical double copy, but it'll be true for what we're working with today. So if you're wondering why they've been omitted, this is why. Okay, so this is the very basic setup, just for people who are familiar with various gravitational solutions. Of course, examples of things that we can write in the Kerr-Child coordinates are fairly broad, but most of them have a fair amount of symmetry. So we can write, for example, the Kerr black hole that way, or of course, Schwarzschild black hole, but also a large family of other solutions, although they are fairly symmetric. So what we'll be using today is actually a version that sort of assumes a little bit of symmetry to begin with in the spacetime. We're going to be working with either type D or type N spacetimes. Yes, I'll describe what that means in a moment. And we'll see how a Weyl double copy looks a little bit natural. So this is going to be due to work by these folk here in 2018. And then more recently, this paper spelled out a lot of details about how to do the type N case. So let me talk about what these type D and type N are. So if we rewrite the Weyl tensor for the gravitational background in a spinor notation, so here I've taken the Weyl tensor W and I've rewritten it with these melding forms here in spinor notation. Well, once I've gotten to a spinor, then I can decompose that spinor into a product of single spinors here, where the single, in general, the CABCD can be rewritten as a product over alpha, beta, gamma, and delta. That gives us that there are always 4 principal spinors. Those principal spinors, each one matches to what's called a principal null vector from the perspective of the spacetime. And in general, in 4 dimensions, those 4 spinors aren't related to each other. They're just totally different. But for many special cases, they might align. So for example, in the case of a Kerr black hole, they align in pairs. So we get an alpha-alpha, beta-beta sort of structure because the spinors have aligned in pairs. And this, in type N solutions, such as I believe PP waves are all type N, you actually get all 4 aligning together. So the vectors align, which means you get 4 copies of the same spinor. So we can kind of see, given the structure of the Weyl tensor written in spinor notation here, that it's fairly easy to square root the Weyl tensor here in these cases. So we can write a version of the classical double copy where it's the Weyl tensor that has been rewritten as 1 over the scalar, and then Maxwell spinor twice here. This Maxwell spinor will, we could rewrite it in spacetime as an F mu nu field strength that we're used to. That field strength will solve the equations that we expect it to for gauge theories. And the scalar also will solve the wave equation that we expect it to. Okay, so let's ask a couple of questions about the classical double copy. And I'm going to use these questions as ways to think about how fluid gravity duality can both tell us things about the classical double copy and vice versa. How can we learn more about fluid gravity duality by understanding this classical double copy? So the first question I wanted to talk about is, why is there a spacetime or not instead of just a momentum space version of the double copy? Because we might have expected something to be only doable in momentum space. It's a little strange here that the classical double copy can be done in spacetime. Well, I think at this point that's actually fairly well understood due to work by Chris White and as well as Chacon and Neji, where they showed in 2 papers within the last year, at least a linearized derivation via twistors and the Penrose transform that gave us sort of a reason as to why this classical double copy is showing up from the perspective of the spacetime. And in fact, they also showed, I believe in the same 2 papers, there's a type 3 example. So type 3 is when I have 3 of the spinors have aligned instead of 4 or 2 in pairs. Type 3 is when 3 of them align and 1 is different. And they have actually shown in this more recent paper from March that at least at the linearized level, the same procedure should work for generic type 1 solutions. So we might ask, well, can we go beyond the linearized level? And fluid gravity is going to give us a series of physically interesting solutions, all of which are going to be at least type 2, but not necessarily higher. So that means 2 of the spinors are going to align and 2 of them are distinguishable from all the others in the generic case. So it does give us a class of solutions to look at that goes beyond the type D and type N that are already well understood. It also kind of gives us a way to think about going beyond the linearized level. So the in fluid gravity duality, the version we'll use is called the cutoff fluid gravity duality. In a sense, it's nonlinear because it is going to allow us to have nonlinear terms in the fluid equations itself, but it's still a perturbative approach because the gravitational solution will be expanded perturbatively. So it gives us a good forum to ask a version of going beyond the linearized level without having to do the full story, because we'll still be doing a perturbation around a flat background. It's also natural to ask about the ability to build a Weyl double copy in higher dimensions. So some work has been done on this. One of the papers I find most interesting is this one with Montero, Nicholson, and O'Connell from 2018. This paper is actually mostly developing that Petrov type story for higher dimensions in more detail than it had done before, in a way that leans into being able to do a Weyl double copy. So fluid gravity duality is present in 4-dimensional gravity, 5-dimensional, 6-dimensional, whatever you want, it goes on up. So it gives us a nice set of solutions to play with and to see if we can understand what their dual is going to be. And in particular, the 3+ 1-dimensional fluids are much more interesting from a fluid dynamics perspective than 2+ 1-dimensional fluids. And because the fluid gravity duality adds a dimension, 3+ 1-dimensional fluids are actually in 5-dimensional gravity. So if we could understand how a 5-dimensional version of the classical double copy works, it would give us more access to more interesting fluids and vice versa in both directions. Okay, so I've given a little bit of an overview about the classical double copy via the Weyl case. Now I want to take a step back and review the formulation of fluid gravity duality that we'll be using in the rest of the talk today. And then we'll move back into using the Weyl double copy to discuss these fluid solutions. So the history of the fluid gravity duality goes back quite a ways. It began with a prescient thesis of Thibault de Moor in 1978. And basically what it shows is that fluctuations of a black hole horizon act like a viscous fluid. They obey something like a fluid equation. Thibault actually in 1978 was able to calculate that the fluid viscosity is going to be 1/16 pi g. And of course, they knew the entropy density as well. So if you do the division yourself, you can get this celebrated eta over s as 1/4 pi limit. The division wasn't done back in 1978, but I think it's simple enough to do from their work. We can consider that the beginning of this limit. But that work and its follow-ups, which became known as the membrane paradigm, are always considering fluctuations at the black hole horizon itself or at a stretched or apparent horizon just outside of that. So we're always near the black hole horizon here. And it builds the de Moor-Navier-Stokes equation instead of just the Navier-Stokes equation. So it's a slightly different equation than we would normally use for fluid mechanics. If we speed forward to a little bit after the year 2000, we get to fluid gravity as it shows up in the context of ADS-CFT. So in the context of ADS-CFT, Polycastro, Son, and Sterinutz showed that the hydrodynamics in n=4 super Yang-Mills is replicated both on the CFT side and the ADS side. Again, they found this eta over s is 1/4 pi bound. And the work that they were doing was really thinking about what's going on at ADS spatial infinity, as opposed to the membrane paradigm, which is going close to the horizon, because they're thinking about the CFT perspective of this fluid. And of course, it requires a fair amount of information in order to build up ADS-CFT, which gives us the fluid limit that gives us fluid gravity duality in this context. So the approach I'm going to talk about, I'll call it a Wilsonian approach today, is work with me as well as Irene Bredberg, Slava Lysov, and Andy Sturminger, about 10 years ago in these two papers. And what we showed is instead of working at the horizon or at some ADS boundary, we're going to work at some cutoff surface in between. And we're actually allowed to move where this cutoff surface is as long as we take our scale appropriately. And we're going to relate solutions of the actual Navier-Stokes equation, as long as it's incompressible, to solutions of the Einstein field equation here. So we begin by fixing the cutoff surface in this diagram. It's this blue line here that's going to be our R=RC cutoff surface. And we'll insist that when we perturb it, we're going to keep this cutoff surface Ricci flat. Waves are only going to be allowed to go infalling into our horizon here at R=0. And when you do this, you find that the extrinsic curvature on this cutoff surface becomes a fluid stress tensor, as long as you take an appropriate hydrodynamic limit. So let me describe what that hydrodynamic limit looks like. First of all, our background metric in this first line, this is Rindler space in ingoing Eddington-Finkelstein type coordinates. And then each line subsequently is going to one higher power in epsilon, where epsilon is going to be the parameter that gives us our hydrodynamic limit. So this is arranged such that the velocity itself of the fluid needs to go like 1 order in epsilon. The pressure needs to go like 2 orders in epsilon. And derivatives with respect to spatial directions will go like 1 order. Derivatives with respect to time directions will go like 2 orders. This is a gradient expansion here. And there are actually higher order terms here. There is an extension of this with Taylor and McFadden, and I don't remember who else was on that paper, sorry, several other people following our work. There was an extension of this to higher orders, but today we'll only use these first few orders, so we won't need more than this. We can check from this metric, indeed, when I set R equals to RC, and I take the induced metric on a constant R surface, so I lose terms like this, I recover just my flat metric. The constraint equations at order epsilon squared will give us the constraint gravitational equations on the R equals R surface, R equals RC surface will give us incompressibility for our fluid. And the constraint equations at the next order will give us the Navier-Stokes equations written here with a viscosity set by the location of our cutoff surface at R equals RC. And then you can show, if you test it, that the Einstein equations, the other Einstein equations here besides the 2 I mentioned, are solved up through order epsilon to the 4th in this limit. And as I said, is extendable to higher orders if you wanted to do so. So I want to highlight a couple of features of the cutoff approach that'll be useful for us today. The first is that it doesn't require ADS, but it is connectable to the ADS approach. In particular, this paper builds that connection. So we might actually want to think of this as perhaps it's a toy case to test how, at least in the classical language, the double copy can relate to ADS CFT, because we understand how fluid gravity in this cutoff approach relates to fluid gravity in ADS CFT. So it might be able to give us a connection. It is extendable to higher orders. Here are the 2 papers that I was thinking about that do that. The hydrodynamic limit that I've described here can actually be recast instead as a near horizon limit. So if I don't restrict the fluid and to be in this hydro limit, and instead I take my R equals RC cutoff surface and I push it towards the horizon, you recover exactly the same physics, just in slightly different coordinates. Importantly for us today, the feature that we'll need from this is that the space-time turns out to be algebraically special. So generic 4-dimensional fluids, the gravitational duals to them are Petrov type 2. This means 2 of the spinors align and the other 2 are free. Through order epsilon to the 14th, we actually showed this back in our second paper in 2011. That order epsilon to the 14th sounds really impressive, but please don't be overly impressed by it. The invariant that we're calculating that gives us that is actually, because of the form of the metric, automatically 0 through order epsilon to the 12th. So we've actually only gone 2 extra orders in epsilon here. It can be forced to slightly more orders to be algebraically special. And if I make the fluid more restricted, it turns out I can actually make more special spacetimes. So there will be a class of fluids, we'll talk about them in a moment, that will give us type D, and an even stronger class of fluids that will give us type N, so that we'll be able to build their classical double copies easily. So let's talk about what those particular fluids are. It's possible to prove algebraic speciality by picking a basis in which to write the Weyl tensor. Weyl spinor. We're going to expand it in these Penrose scalars, size 0, 1, 2, 3, and 4. If it can be arranged such that only psi 2 is non-zero and all the others are 0, we'll have a type D spacetime. If it can be arranged so that psi 4 is non-zero and the others are all 0, then we have a type N spacetime. And you can kind of see that if I cover up these first four, indeed, this obviously factorizes into the same spinor 4 times because the O's are all the same there. So in general, for fluid dual spacetimes, if we pick a good frame, we can set psi 0, psi 1, and psi 3 to all be 0, at least up through order epsilon cubed. We're left with a psi 2 that's non-zero and a psi 4 that's non-zero. So in these algebraically special fluid dual spacetimes, I'm going to restrict to the time-independent case, although all of this can be done with time dependence. It doesn't change the physics much, so we won't discuss it today. What we find is that type D fluids are fluids that have constant vorticity, and type N fluids are fluids that have potential flows. So let me say a little bit more about the type D fluids, because I think they're a particularly interesting case. In this case, we're going to insist that only this psi 2 is allowed to be non-zero, and it actually turns out that it has to be a constant. If I allow this vorticity here to vary with space, if it isn't perfectly isotropic, then I will end up with a non-zero psi 4 that I can't avoid. So I won't be in type D, I'll be in type 2, which is much harder to do. So we're looking here at if I build what the F mu nu is, and again, it's easy to take the square root in this particular case because only psi 2 is present. I can build what my gauge field strength dual looks like. And it ends up that it looks just like sort of the field along a solenoid. So that's what I've drawn for you here. These yellow arrows are supposed to be the electromagnetic field that we've got here. And the S itself, the scalar, turns out to be kind of trivial. It's just a constant. So it does solve our field equations, but maybe not in the most interesting of ways. How does this relate to the fluid that we've got? Well, the fluid is actually supposed to be represented by these blue arrows in the background. So if I pick a particularly nice choice for this theta, I have a little flexibility in making it there, then I can get that this fluid is this electromagnetic dual looks like the field from a current on a giant solenoid. And the fluid solution itself, if we go back and think about what fluid gave us constant vorticity everywhere, well, constant vorticity everywhere fluid is like I've taken a giant cylinder, I've insisted that there's no slip conditions at the wall, I stuck the cylinder in some water, and then I rotated it. So the fluid is just rotating along with this cylinder as I go around, which kind of gives us a nice picture. It looks a little bit like the electromagnetic current that would be producing this field in what the field dual looks like.
Cynthia, you have 5 more minutes.
Thank you. Okay, so we should mention that there is a bit of a technicality here with this fluid is only going to work in the hydrodynamic regime. And that hydrodynamic regime is actually restricted by the location here. So we need to keep our X and Y large in order for this fluid solution to be kept in the hydro regime. This is actually fixable by doing everything in the near horizon expansion instead. I won't repeat that here because you end up with the same physics. In the type N case, the story instead ends up being that the fluid is a potential fluid. So the flow is just the gradient of some scalar. And then the single copy and double copy story, or zeroth copy and single copy story that match the double copy that is this gravity, the single copy gives us an electromagnetic field that's sort of just like the background to have a fluid solution in the first place. And the zeroth copy is the thing that carries the information about our potential. So the potential fluid ends up, the potential that's the scalar ends up just really living in that zeroth copy scalar of our fluid. So let me give just a quick summary slide. We already talked about how the type D fluid, which are these isotropic arrangements with constant vorticity. We have this nice picture of the no-slip cylinder fluid matching to the field coming from a big solenoid with the current being proportional to the vorticity of the fluid. And then in the type N fluids, these are the potential fluids, and the potential lives in the zeroth copy scalar, which seems to match with what we might have expected for where a scalar object should be living here. So a natural question to ask is if we can generalize to all fluid dual spacetimes, because of course the generic fluid dual spacetime has both a psi2 and a psi4. It isn't easy to do this in the sense that if you simply try to build up a single term factorization here, it's not actually possible to factorize with just a single term. So the classical double copy here must consist of at least 2 terms. So one possible way to fix this is to build up something that takes multiple terms. And again, I want to highlight these papers from within the last year using a twister method. If we knew the correct Penrose transform to build the fluid dual solutions, the method these guys proposed does give us multiple terms in the proposed double copy version. Let me give you a couple more details about the problem with what happens with these in specific. I'm going to skip this slide, but I did want to show you guys a couple of examples of fluids that have difficulties. So one is Couette flow. Couette flow is the flow between 2 parallel plates when the plates are moving with respect to each other. And so it discusses how the fluid in between them flows. This Oseen-Lamb vortex is time dependent. You can see it has this time dependence down here. And it also has a sort of exponential behavior. This is the exponential integral here. So when you take derivatives of this, you get just an exponential fall off sort of for the scale of your velocity in the fluid, which is why it's like a vortex. It's got a peak at one particular location. And it is a dissipating thing. It changes over time. Both of these are examples of fluids that don't actually give us a good factorization. We have a couple of different ways we can try to factorize. We could try to factorize by making the 2 fields different from each other, the 2 electromagnetic fields that would build up the gravitational when you multiply them, trying to make them the 2 different choices for how we do them. In the case of Couette flow, they actually have a very similar problem. The field strengths work, but the scalars don't. And unfortunately, this Oseen-Lamb vortex doesn't work at all. So it really does seem to be the case that we need to include extra terms. We can't just factorize in a single double copy term. We'll have to have a sum of terms. And those of you guys who are familiar with the double copy story from quantum amplitudes, of course, this is very natural to have. And as I said, it also comes naturally out of the tensor story. So let me take just 1 minute to talk about these future questions. I think I've already discussed that this extension to a sum of terms might be a nice way to try to solve the problems we're having with type 2 fluids. And that this twister story via the Penrose transform might be a good way to figure out what those terms should look like. I mentioned also that the Navier-Stokes fluid duals that we built here could give us a nice way to start approaching some nonlinear terms, but it is still a perturbative approach. So it's still tractable, let's say. We might want to try to go to higher orders in epsilon or lambda. As I mentioned, we'd only gone to some fixed order here and hadn't kept track of the extension. Another interesting question is to ask if this can be related to other fluid gravity dualities, for example, in the large dimension limit or in the context of ADS-CFT. And I am also interested in trying to do the Weyl double copy in larger dimensions, partially because it gives us access to a 5-dimensional double copy that will allow us to discuss 3 + 1-dimensional Navier-Stokes fluids, which are the much more physically interesting fluids to begin with. And then I also wanted to mention some forthcoming work with my student Samarth Chawla, which will be talking about separability in general spacetimes as a double copy for generic dimensions. So I think that is all that I have for you guys today. Thank you for listening.
Thank you, Cindy. Let's unmute our microphones. So thanks, Cindy, for this nice talk. And please, people, go ahead and ask your questions, raise your hands.
I have a question.
Yes.
Can you hear me, Cindy?
Yes.
Ah, great. Thanks for a nice talk. What I wanted to ask, do you also, I mean, does the double copy that you do for the fluid dual spacetime teach you also something about, you know, because as you said yourself, right, the fluid lives in 1 dimension less. So does it imply something special for the non-gravitational quantum field theory, that has the corresponding fluid description?
I think that's an interesting question. I think it's a little hard to access it until we can do a more generic set of fluids.
No, I can see.
Because the two kinds of fluids that we can do for sure right now are really quite restrictive, which doesn't really give us access to most of the dynamics you'd be interested in the fluid aspects of field theory.
Because just to say, like, maybe I got carried, well, it's a very beautiful story, but when I saw your title, I thought that, say, applying the double copy in the bulk gravity would almost teach you that there is a certain avatar of the double copy in the dual quantum field theory. But okay, that's not yet the case. Say
that would be great. I'd love that. Okay. I don't think I can give you strong evidence, at least in the fluid regime, for that at this point.
Okay, but super interesting. Thanks a lot. And yeah, okay. And my other question is, do you have any ideas about the large D case? Indeed, it might be, as we know, there are many beautiful simplifications there. It's probably easier than generic D equals 5 or 6.
It is probably easier than generic D, although I will mention that I think there is a lot understood about the classical double copy for generic dimensions for particularly simple solutions, which does include the Schwarzschild black hole. So one can actually, in the classic large D limit is in the Schwarzschild case. So one can actually already ask those questions. But I think then you're wanting to perturb about this background. And I'm not sure how well the classical perturbations in the large dimension limit would be analyzed. I think it's a good question. It's worth asking. Yeah. I do see that Ricardo has his hand up.
So let Ricardo ask his question.
Thank you. In the type D fluids, how many parameters does the fluid have?
It really just has, if we're insisting it be time independent, it really just has one. It has just the vorticity. That's the one parameter that we have.
If you write that in a sort of Plebanski-Demiansky way, I don't know. So I mean, the spacetimes are fixed up to a fixed number of parameters, type D. What does that vorticity correspond to?
Oh, that's a good question. Yeah, I'm not actually sure. I haven't thought about it. I'll have to get back to you on that. It's a good question. It must have to do something with rotation. So I don't know if it would end up looking like something like a nut charge or a rotation parameter at infinity, but it's going to have to do something with that. I'll have to look at it and see. That's a good question.
Thanks.
Okay, so we have to go on. So let's thank Cindy again. Thank you, Cindy.